Hi, my name's Jenna and this is my Physics Lab Report 5 on Faraday's Law. The purpose of the lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil to model the magnet-tube interaction computationally and to compare the computational predictions with the observed data. For a preview, the system was the phone, the magnet, the foil, and the meter stick. The surroundings were everything else. And for the results, the experimental average time was 1.254 seconds, and the computer model time was 1.188 seconds. Some important concepts to understand are Faraday's law, or magnetic flux, and magnetic flux is just all of the magnetic field throughout a certain area. It is the integral of the magnetic field times the perpendicular vector and the area. And as you can see here, the derivative of magnetic flux is related to EMF, and the negative sign is Lenz's law. And then we also need to know Biot-Savart law, which is just magnetic field for a moving particle. And then finally, Newton's laws and position update, just to get position update formulas. After doing the experiment, the trial results were as follows. 1.24 seconds, 1.28 seconds, 1.27 seconds, 1.25 seconds, 1.23 seconds, an average time of 1.254. The tube was a 0.3 meter by 0.006 meter tube. The inner radius was 0.02 meters, outer was 0.032, and the mass of the magnet was 0.025 kilograms. And to answer the checkpoint questions throughout the experiment, why can't we use a steel pipe as a tube? And the reason for that is magnetic interference. There would be the fields interacting with the magnet and skewing our results. And then the other question, what happens to the magnet and how does this compare to a magnet falling in free space without a tube? The magnet in the tube falls slower than it would in free space because of the forces and the current slowing it down. For the computer model, I'm just going to quickly go over it. Where does it start? Okay, here I just plugged in my measurements for the tube that I said before. Up here, or where's the next? Sorry about that. Oh yeah, here I put in the mass and the dipole moment of the magnet that was found from lab 3. Here, I edited the function for the dipole magnetic field, just doing r mag, r hat, and then the formula for field, just plugging in numbers. Let's see. Down here, once again, just plugged in numbers for the flux formula. And then on this next slide, I just made the gravity vector and then calculated the net force by adding the gravity and the magnetic force together. And then finally over here, just position and velocity update using Newton's second law. And finally, down here we have our results. This is the velocity versus time graph, and as you can see, it's pretty constant right here. And then the time that it spent in the tube, which was 1.188 seconds. Interpreting the simulation. So the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. The red and blue indicate current flows in opposite directions, and I had to determine which one was clockwise and which one was counterclockwise. The red one was counterclockwise and the blue one was clockwise, and basically these two currents just work together to slow down the magnet as it falls. What happens to the dynamics of the system if you flip the magnet around? It would work the same, the currents would just be flipped, but it would still be the same time, same speed. How does the total time in the tube of my real-world system compare to my computational one? My real-world was 1.254 seconds, and the computational was 1.188. So in the real world, it took a little bit longer to fall, but ultimately at the same time. And how could I have made my computational system more accurate? I definitely could have had more coding experience and also accounted for air resistance and drag. And then finally, what does the shape of the velocity versus time plot tell about the forces acting on the bar? As we can see here, it starts with a little wavering force, but then it's constant. Well, the velocity is stable because it's not accelerating. So, and then it goes away. So finally, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Forces would become stronger and ultimately halt the magnet from falling in the tube at all. And then what if holes or slots were cut in the tube? How would this affect the ring currents in my model? Holes would alter the flow of the current through the body, decreasing its strength of both the force and the current because there's ways for it to escape. Finally, to account for error, as previously mentioned, I definitely have limited coding knowledge and resources, so if I was better at coding, I could have made the experiment or the computer model more accurate towards reality. There also could have been error in recording the experimental results. I didn't have the most precise camera or timing method. I kind of just recorded it and eyeballed where it went in and where it fell out. Once again, there could have been air resistance, making the magnet fall at a slightly different rate, and finally, nearby magnetic fields. Thank you.